Hello, and welcome to episode 5 of our series Back to Basics Season 2. In today's episode, we are going to talk about predictive analysis and simulation, two very important topics in the human-based decision support pillar. From Wikipedia, predictive analytics encompasses a variety of statistical techniques from data mining, predictive modeling, and machine learning that analyze current and historical facts to make predictions about future or otherwise unknown events. A simulation is the imitation of the operation of a real-world process or system over time. Simulations require the use of models. The model represents the key characteristics or behaviors of the selected system or process, whereas the simulation represents the evolution of the model over time. Often, computers are used to execute the simulation. In the session about statistics, we have started discussing inferences. In other words, we saw how we can estimate an output based on a set of information. This is the start of a predictive approach. The goal is now to predict an output, possibly in the future, based on a set of inputs. As introduced, this started with actuariate, which predicts the coverage of a risk, death for example, based on the information collected on people. Age, gender are important factors, as well as smoker, non-smoker, if you have had a cancer before, etc. The output of this kind of approach is the probability to die for each group of population. Based on this, insurance rates can be calculated to cover the risk of death for the whole population. Predictive analytics is now widely used for many other purposes: marketing campaign targeting, fraud prevention, weather forecasts, and more. Here are some milestones around predictive analytics, but by no means an exhaustive list. From 1939 to 1945, the Manhattan Project team utilized Monte Carlo simulation, all manual, to predict the behavior of atoms during a chain reaction. The results being the creation of nuclear bombs. In 1950, the ENIAC, Electronic Numerical Integrator and Computer, ran a set of mathematical equations to predict the airflow in the upper levels of the atmosphere, leading to the use of computers to help forecast the weather. In the 70s, the development of more performant computers has led to an increased use of predictive analytics. Insurance companies and banks have used it exhaustively to prevent risks. Since then, predictive analytics has boomed with the amounts of data that has been made available. It is one of the components of artificial intelligence. We will see this later on. The general principle of predictive analytics is to systematize the prediction by developing a predictive model on known data. Predictive analytics uses datasets, which means structured data. The predictors are the set of columns from the dataset used to predict the target, which is what we want to predict. The way it is performed is the following. We have two phases. Phase 1, from a dataset that contains predictors and a target, we estimate a predictive model by using a given algorithm and an optimization metric. This is called the training phase. Phase 2, we execute the predictive model on a set of new predictors to get the prediction. This is called the production phase. Let's take an example to illustrate this principle. If we want to predict if a customer is likely to churn or not, we will use a target which describes whether a set of customers has churned or not in a certain point of time. The predictors describe the customers as they were before that time. General characteristics, behavior, etc. We use a classification algorithm, let's say a decision tree, with optimization metrics. Here, for example, entropy and information gain. We end up with a predictive model. Here, it would be the decision tree. We then can use a data set where we don't know if the customers will churn or not. Apply the decision tree, the predictive model, and then we get a probability for each of the customers to churn. Predictive analytics consists of a set of techniques which are used depending on the context. Regression aims at predicting values, the amount each customer might spend next month, for example. The target is a number, and it is estimated for a set of individuals. An example could be estimating the height of a set of people. Time series aim at continuing a signal. For instance, when we look at sales for a company, we can follow it over time. Forecasting sales is a typical use of time series where for each granularity level, being region, shop, etc., we want to get the expected sales for a given future, let's say here 3 months. The output is a single number or a set of numbers referring to the same entity. Classification aims at giving the probability that an entity belongs to a certain category. We consider two main types, which correspond to different algorithms approach, binary and multi-category. Binary classifications are the most widely used. They answer a simple question: will the target event happen or not? An example illustrating is churn prediction. Will the customer leave the company or not? Multi-category classifications correspond to the other type of problems. What is the likelihood that a customer will choose a specific brand among a set of brands? Or what is the preferred color of someone? Recommendation engines are coping with many classification models to produce in case of product recommendations from a large catalog. They are based on past transactions only without any other description. They provide a probability that a customer would buy a given product by looking at what he bought previously. It is used to predict which products to recommend. Clustering is at the boundary of predictive analytics, as its purpose is to group entities that have common characteristics. Algorithms specifically designed for that are used, such as k-means or Kohonen self-organizing maps. Many algorithms are used to perform predictive analytics. The goal is not necessarily here to provide an exhaustive list, but to give a few examples. There are a few families of algorithms. Regression with linear, logarithmic, and ridge regression. Bayesian. Decision tree with decision tree, random forest, gradient boosting, and neural networks. Time series, where time dependency needs to be modeled, have their specific algorithmics, ARMA, ARIMA, etc. The same goes for clustering. Some of these algorithmics require specific data formats to perform best and to handle missing data and outliers in specific ways. Defining the predictor to be used is as much important as with algorithms. The quality of the prediction mostly depends on the amount of information related to what we want to predict is available in the dataset. Creating new columns is therefore extremely important and usually represents a big part of the project. It is referred as to feature engineering. The main ways to create information include creating aggregates, the time spent on the phone by the customer, for instance. Ratios, the percentage of domestic versus international calls. Transformations, we put everything in the same currency, for instance. Groupings, we group brands of phones, types of contracts, etc. If non-structured data is used as input to the predictive project, it needs to be structured, potentially using deep learning techniques for texts and images, or transformations, vibration with Fourier transform, etc. Predictive models need to be robust to be used in production. This means they constantly need to reproduce the same level of prediction. In the training process of the model, this is verified on a validation dataset and usually also tested on a test dataset. Non-robust models that perform much better on training than on test sets are said to be overfitted. As expressed earlier, the predictive analytics systematize predictions in a known data space. When predictors' value were never observed, we are outside that space and therefore we say we extrapolate. Here is an example of the problematic of extrapolation. The variable 1 is related to the target. What happens for its upper values? Can we continue the curve? Usually, we don't know. So conservative approaches can be applied, such as take the prediction from the uppermost known value. But others can be taken too. Extrapolation should generally be avoided as confidence in the results is much lower. A predictive model is an image of the dataset it was built on. As time passes by, it is likely that data will change. Range, distribution, relation between the predictors, etc. Therefore, the model might produce predictions which are increasingly wrong. In fact, the model is not robust in time. For this reason, we need to control the model quality over time. In other words, measure how the model predicts when the target values are available. When prediction quality drops, the model needs to be retrained. This has a strong impact on predictive analytics projects, which are not punctual projects, but ongoing until the model is dropped. Doing simulation with predictive models is very appealing. From a set of predictors, we can change the values, execute the equation via the model, and get the prediction in a what-if approach. Of course, all the above applies, especially extrapolation problems. Nevertheless, being able to simulate has great business value. SAP helps companies with predictive analytics and simulation in software such as SAP HANA and the around 90 algorithms embedded in SAP HANA, but with SAP Analytics Cloud as well, and others, as the business value generated because of accurate and relevant predictions and simulations is crucial in today's world. External algorithms, standard and or self-developed ones, can also be integrated in SAP's solutions to extend the capabilities of the standard software solutions. Now that we know a little bit more about predictive analysis and simulation, I will see you next time when we talk in the next episode about data visualization and dashboarding.